Alright, so we're starting chapter 3 today. So we'll cover naming covalent compounds. We'll probably start talking about ionic, but we won't get all the way through ionic, so we'll continue with that on Thursday. What is due this week are the chapter 3A questions. So chapter 3 is longer than chapter 2, so it's going to take us 2 weeks to get through it. So you have 2 separate homework assignments for chapter 3. So those are already posted for you to give a try, and then there's also the discussion on anything that we talk about in class, or anything on the PowerPoints, or anything in the book that you're reading. So don't forget to do that. All right, so let's get started. We're going to start by talking about covalent bonds. So in chapter 2, we kind of ended the chapter talking about electrons, valence electrons versus total electrons. So when we talked about valence, we said those were the electrons in the outer shell. Those were the electrons that are involved in bonding. So when I'm talking about covalent bonds, and later when I talk about ionic bonds, it's the valence electrons, those outer shell electrons, that we're talking about. Okay, so there are 2 different types of covalent bonds, polar covalent and non-polar covalent. So we're going to do a calculation to figure out which is which. Also, when you're looking at a covalent bond, they're typically between nonmetals and semimetals. So it could be 2 nonmetals together, it could be a metal and a semimetal, or it could even be 2 semimetals together. So what I'm talking about is the periodic table, what we looked at last chapter. There's a zigzag line separating the metals from the nonmetals. So the metals were to the left of the zigzag line, the nonmetals were to the right, so in the upper corner. And then anything touching that zigzag line, with the exception of aluminum, was a semimetal or metalloid. So semimetal and metalloids are the same thing. So we're just looking at a small fraction of the periodic table when we're looking at covalent bonds. And you'll see when we do the examples, all the atoms, all the elements present, they're all either nonmetals or metalloids in the examples that I have up here, and the examples that I have in the PowerPoints as well. So some of these bonds are polar covalent, which means they're unequal sharing of the electrons. So with covalent bonds, they're sharing electrons. There's no transfer, there's no ions involved. So sometimes they share those electrons equally, and sometimes unequally. So when they share them unequally, we call it polar. And the reason they're sharing it unequally is because one atom is more electronegative than the other. Electronegative means it wants the electron more. So since one of the elements want the electrons more, they pull those electrons closer to them, and so they take more of that negative charge. For nonpolar, this is where they're sharing them equally. So this is when the electronegativities are similar, and so neither atom wants the electrons more, so they share them equally. Now there are some pictures on the PowerPoints, diagrams where you can actually see what that looks like between the 2, whether they're sharing equally or unequally. What we're going to do on the board is the calculation portion. So this is a calculation we're going to use to figure out the type of bond. So this triangle is a delta sign, it means change in, and that En means electronegativity. So we're calculating the change in electronegativity. So if it's a large electronegativity difference, it's going to be polar, and they're not going to share it equally. If it's a small electronegativity difference, it's going to be nonpolar. So to figure it out, we look at the 2 atoms that are present in the bond, find their electronegativities on the electronegativity table, and subtract them. Notice we have bars. These are the absolute value bars, just like we saw when we did percent error calculations. Okay, what that means is it needs to be a positive number. If you get a negative, just change it to a positive. So what numbers are we using? There is a handout in the week 5 folder. It has electronegativity table on the top, and then it has polyatomics on the bottom. So we're going to be using this periodic table, and it's different than the normal periodic table because it just has the symbols and then a number below. And the number below is the electronegativity of that atom. So to figure it out, we look at the 2 atoms bonded, find their electronegativities, subtract them, and then whatever our answer is, we're going to fit it in this scale. So if it's 0.5 or less, it's nonpolar, so a small electronegativity difference. If it's above 0.5 but below 1.9, then it's going to be polar covalent. If it's higher than 1.9, it's ionic. Now we probably won't see this, and we probably won't even use this method to find ionic compounds. Ionic compounds are usually metals with nonmetals, so we can just look at the atoms present, where they are in the periodic table, and figure out if it's ionic or not. We mainly use this calculation just to distinguish between nonpolar and polar. Okay, so let's apply this. Let's see how it works. So looking at the first example, I have silicon-chlorine bond. So silicon being a semimetal, a metalloid, and then chlorine being a halogen in group 17, a nonmetal. So you just look up the elements present and then subtract. So we have activity. What is silicon? 1.90. And then looking at chlorine, we get 3.16. Can you subtract those for me? Okay. So notice when I subtract these, I'm going to get a negative number, but since we have those absolute value bars, we just change that negative sign to a positive sign. I get positive 1.26. So using this number, we see where it fits. And this is actually quite a large electronegativity difference. So it's between 0.5 and 1.9. So we would classify this compound as polar, or this bond, I should say, as a polar covalent bond. So notice, looking at the electronegativities, that chlorine was the 3.16. He's more electronegative than silicon. So if you see from the PowerPoints, that means he has a delta negative, and silicon would be delta positive. So what that means is chlorine's more electronegative, it wants the electrons more, so it's pulling those electrons closer to it. That's why it has a partially negative sign, leaving silicon with a partially positive sign. Now these aren't ions, this isn't transfer of electrons, it's just partial charge. All right, so let's try the next one. We have sulfur-hydrogen bond. So same thing here. Let's look at their values. Sulfur is a nonmetal, 2.58. Hydrogen is also a nonmetal. It is over here by the alkali metals, but it's a nonmetal, and that was 2.20. Subtracting those, I'm going to do that one without my calculator. Hopefully, I won't get it wrong. 0.38. So very small electronegativity difference, right? They're very similar to each other. So 0.38 is less than 0.5. So that means they're sharing those electrons equally, and it is a nonpolar. So since it's nonpolar, we don't have a separation of charge at all. There's no partial positive, no partial negative. They're sharing them equally. Now these next two, we're going to calculate the same. They just look a little different. So for instance, Br2. This sub 2, that tells me how many atoms of bromine are present in this compound. So it's the same as if I would have written Br-Br. Okay, 2 atoms of bromine attached. So we do the same calculation, except for this time we have 2 atoms of the same element. So you can probably guess what the answer is going to be, but let's show it on the board anyway. Bromine is 2.96. And then we're going to subtract it from the other bromine atom, which is also 2.96. So we get 0 as the answer. And that's the lowest electronegativity change that you'll see. We can't go into the negatives. So since it's 0, it's nonpolar. They're going to share those equally. All right, now this next one. NH3. So we have nitrogen and then 3 hydrogens around it. Now, when you see one like this and they're asking, okay, what is the polarity of the bond? Is it a polar covalent or non-polar covalent? they're asking just between the nitrogen and hydrogen. So we haven't talked about structures yet. We talk about that, I don't think we'll talk about that till chapter 4. But what this looks like is it's a nitrogen in the middle with 3 hydrogens around it. So when we're calculating the bond itself, we're just going to look at one of these nitrogen-hydrogen bonds. It's just this here. So it's still the same. We just have 2 atoms, their electronegativities, and we're subtracting them. Because each of these are going to be the same polarity. So change in electronegativity, looking at nitrogen, E is 3.04. And then hydrogen, we just did up here, 2.20. So 0.84, so that's above 0.5. So this is going to be a polar covalent bond. So if it's polar, that means it's because it has a large electronegativity difference. So we're going to see partial charges. So where are those partial charges going to be? Well, you need to look at the numbers involved. So nitrogen has a higher value than hydrogen. So that means nitrogen is more electronegative. So nitrogen would have the partial, I always draw this delta sign kind of funky, partial negative, because it wants those electrons more, it's more electronegative. And then hydrogen would be this partial positive one. Questions on this? Make sense? So we're going to continue with covalent, but now we're going to name covalent compounds. So I'll leave the definition of covalent up there, and we'll just look at how to name them. So with covalent, we use prefixes. What I've written in green there is the basic format for naming a covalent compound. So once you identify the compound as covalent, which you can do that by just looking at the atoms or elements involved in the compound. So if all your atoms or elements are either nonmetals or semimetals, it's going to be a covalent compound. So once you know it's a covalent compound, you know that you're going to need to use prefixes to identify how many atoms of each element. So for the prefixes, and I have a list of these on the PowerPoints as well. 1 would be mono. If you have 2, it would be di, 3 tri, 4 tetra, 5 penta, 6 hexa, 7 hepta, 8 octa, and then 9 nona. So we're not going to go above 9. So what are those used for? Well, the easiest way to explain it is through an example. So I'll throw out a few examples here. We have S2O4. Four different examples. So these are all covalent compounds. How do I know that? Looking at the elements involved, these are all either nonmetals or metalloids. Okay. Sulfur, oxygen, both of those are nonmetals. Both of them are actually in the same group, they're in group 16. So if I know it's a covalent compound, I know that I need to use prefixes. What are those prefixes for? these numbers here, the subscripts. So remember, these numbers tell us how many atoms of that element are present. So there are 2 sulfurs and 4 oxygens. So when I'm naming this compound, I indicate how many of each atom by using the prefixes. So for instance, sulfur, there's 2 of them. So I'm going to start by writing di. Di what? Disulfur. I'm saying there are 2 sulfurs. So the first element present, you write that element name just how it's represented on the periodic table. For the second element present, in this case oxygen, I'm going to do a prefix for that guy as well. So since there are 4 of them, it's going to be tetra. Now the second element is different, so I'm not going to write tetraoxygen. For the second element present, you're always going to add an IDE ending. So instead of writing oxygen, I'm going to write oxide. And I also have a list on the PowerPoints showing how all of the nonmetals change when they have an IDE ending, just so there's no confusion. Because I know some people want to say oxygenide, but that's incorrect. It's just oxide. Same with nitrogen. It changes into nitride instead of nitrogenide. All right, so let's try this next example. So based off of that outline, I need a prefix. I need to start with a prefix. So here, there's no numbers. So if there's no numbers, no subscripts, you just assume that there's 1. Okay, so that means there's 1 carbon and 1 oxygen. So when we're talking 1, we're using the mono. So for the first one, it'll be mono, and then C is carbon. So you just write that just how it is on the periodic table. Then for the oxygen, there's also 1, so we start with the prefix mono. And then just like up here, we add an IDE ending to oxygen, so it would be oxide. Now if you read this name, it sounds a little funny, because you've probably heard of this compound before. Monocarbon monoxide. Well, we don't call it monocarbon monoxide, we just call it carbon monoxide, just like carbon dioxide, right? So this is where there's an exception. Like there's always exceptions to everything in chemistry, right? And that exception is on the first element. So if the first element is mono, or element has 1 atom, don't put the mono, don't use prefix. This is the number 1. So if the first element present has only 1 atom, you don't use the prefix. So carbon is the first element present. It has just 1 atom, so we're not going to use the prefix. Notice though, the second element has 1 atom, but we did use the prefix. So this, leaving the mono off, only applies to the first element present in the compound. And we're going to see that in this next example too, so we can apply it again. So in this example, we have silicon and chlorine together. Well, silicon doesn't have a number after it, so we assume there's just 1. Well, since silicon is the first element present, and it has just 1 atom, we are not going to put the prefix. So we're not going to write mono, we're just going to write silicon. Now the chlorine, it has 4. So we do need to put a prefix for the chlorine, and since it's 4, that prefix is tetra. Chlorine being the second element, so we need to add an IDE ending, so chlorine becomes chloride. So silicon tetrachloride. And there usually isn't a giant space between both. I'm just trying to keep them separate. In capitalization, you don't have to capitalize either. All right, let's do the last one. So C3H8. Now there are some common names for this. For instance, if you look this up, I think the common name is propane. But we're going to name them systematically using the prefix names. So 3 carbons tells me I'm going to start my prefix with tri. Start my name with the prefix tri. Carbon first element, just name it from the periodic table. Then for hydrogen, there's 8 of them, so I'm going to use the prefix octa. And hydrogen, we need to add an IDE ending to it, so hydrogen becomes hydride. And I have a practice worksheet in the week 5 folders. Yeah, so you can get more practice with naming. Because a lot of this, like the IDE endings, the prefixes, it's just practice. You know, the more you do it, it becomes more natural. So what we're going to do now is we're going to take, so we've taken the chemical formulas, that's what these are called, chemical formulas, and named them. Now we're going to go the opposite direction. I'm going to put down some names, and we're going to figure out what the chemical formula should look like. So what examples do I have? Phosphorus. Why did I decide to capitalize that B? So I have 3 different names. I can figure out that those are covalent compounds based off of the elements present, but also the fact that prefixes are used. So if you see a prefix in a name, it's a covalent compound because we don't use prefixes for ionic, which we'll see in a minute. So to change this into a chemical formula, you need to look up the element symbol for the atoms involved. So phosphorus, you would look that up on the periodic table if you didn't know what its symbol was. And phosphorus's symbol is a P. Then we have a tetrabromide. So this bromide, that's just the IDE version of bromine. So you would look up bromine on the periodic table. It's number 35 in group 17. It's one of the halogens. And the symbol for bromine is B lowercase r. Once you have the symbols, the prefixes are going to tell you what numbers you need to put, what subscripts. So diphosphorus, di tells me it's 2. Tetrabromide, 4, so Br4. So P2Br4, that is the correct chemical formula for that name. All right, so the next one, dinitrogen monosulfide. So this is just nitrogen. So looking at nitrogen on the periodic table, number C, number 7. So N is the symbol for nitrogen. Monosulfide, so sulfide is just the IDE version of sulfur. Sulfur is represented by the letter S, number 16. This is the atomic number. So now we use the prefixes to figure out the numbers. So dinitrogen, di being 2, monosulfide, so mono being 1, but we don't put a 1 there, we just leave it, because then it's assumed that there's just 1 if there is no number. So N2S is the correct chemical formula for that guy. The next one, nitrogen monoxide. Notice, we have nitrogen again, so that's just N, but there's no prefix in front of nitrogen. It's the first element present. So if there's no prefix, what does that tell us? There's just one of them, right? Because we leave the mono off if there's only one. Now the second element present would have a mono on it if there's only one. So monoxide is actually the IDE version of oxygen. So that's how I know the symbol's O. And then the mono part tells me there's just one. And I'm not going to write the number 1, it's just NO. All right. So those aren't too bad just because they have the prefixes to tell us the numbers. Ionic is a little bit more difficult. So let's start looking at ionic compounds. So now with ionic compounds, we're looking at a transfer of electrons. So when we transfer electrons, what I'm talking about is gaining and losing those valence electrons. So if you gain an electron, you become a negative ion, or an anion. If you lose an electron, so you lose a negative electron, you become a positive ion, or a cation. So we're looking at cations and anions together. Now, ionic compounds, we're going to start by looking at metal-nonmetal pairs. Okay, there's other versions of ionic compounds. There's polyatomics, as well as some transition metal ones too. But we're going to start with just main group metals and nonmetals. So the metal portion is going to be the cation, the one that loses the electrons, that gets a positive charge. The nonmetal portion is going to gain the electron and become an anion. So the reason a lot of ionic compounds are a metal and a nonmetal is because opposites attract. We need a positive and a negative together. We're never going to see two metals bonding, in this course at least. It does occur. We're not going to see that happen because they're both positive and like repel. So that's why we're going to see a positive with a negative. So to name it, we're going to use our positive ion we're going to name first. And then the negative ion, the anion portion, we're going to add an IDE ending. Just like we did for covalent with that IDE ending. Okay, now notice I don't have prefixes up here. So there's two examples, two chemical formulas. So let's try to name this first one. Remember, no prefixes. So let me even just erase this so we don't look at it while we're naming ionic. So barium and chlorine. So barium's a metal. It is a main group metal. It's an alkaline earth metal in group 2, down towards the bottom. Chlorine is a nonmetal. So it's a halogen in group 17. So the metal, barium, is going to be our positive ion. So we're going to name him first. How do we name him? Just find him on the periodic table and write the name, barium. No changes. The negative ion, the nonmetal portion, chlorine, we are going to change. Okay? There's two chlorines, but this doesn't matter for naming because we're not using prefixes. Okay? So we're not going to say dichlorine. That would be wrong. We're just going to take the negative ion, the nonmetal portion, and just add an IDE ending to it. So it's going to be chloride. Instead of chlorine, you just change it to chloride. Pretty straightforward.
But there's a 2, and it's 2 chloride. So it's just.
There's 2 of them, but for ionic, we don't use prefixes, so we're not going to say di. And you'll see why when we take the names, because we'll use the charges to figure out what the subscripts are. So we don't need prefixes. With covalent compounds, we need the prefixes because there's no other way for us to know how many of each are present. With ionic, there is. It's a charge thing that we're going to do here in a minute. Should write that. No prefixes. All right, so rubidium. So I almost named it. So we have 3 rubidiums, and it's attached to nitrogen. So the rubidium is the metal portion, the cation portion, the positive ion. Rubidium is an alkali metal, so it's a main group metal in group 1. When I find it on the periodic table, rubidium, which I might be spelling it wrong, just name it exactly how it is. Now, there are 3 of them, but we're not worried about prefixes, so it's still just rubidium. For the nonmetal portion, the negative ion, nitrogen, we just take that and add an IDE ending to it. So nitrogen would become nitride. So if you have the chemical formulas of ionic compounds, coming up with the names is pretty straightforward because you're not worrying about prefixes. All you have to do is add an IDE ending to the second element. So what I want to focus on is going the other direction because that's a little bit more complicated. So I'm only doing 2 examples of that, so we can focus on, given the names, what would be the chemical formula. So beryllium. Lithium hydride. Trying to give myself some room to show the manipulations here. Okay, so these are all ionic compounds. How do I know? Well, first off, I don't see any prefixes, so that would tell me it's ionic. Also, you can look at the elements involved and realize that you have metals now. So for covalent, we don't have any metals in covalent compounds. So let's start, let's be weird and go from right to left instead. So let's start at sodium sulfide. So if I wanted to come up with a chemical formula based off of this name, how do I approach that? I don't have prefixes this time, right? And what we did last time is we found each of these elements on their periodic table and we wrote down their symbol. We're still going to do that. So sodium, finding sodium on the periodic table, it is an alkali metal, so it's right underneath lithium. So sodium's symbol is Na. Well, what about the second portion, sulfide? This is just the IDE version of sulfur. So its chemical symbol is just S. Okay, but we need to go a step further. So we need to not just write down their chemical symbols, we also want to write down their charges. So this is what we talked about in chapter 2. When we went through and we talked about how many valence electrons the main group elements had, and then we also talked about what their most probable ion was. So the alkali metals, group 1, lithium, sodium, potassium, rubidium, cesium, they have 1 valence electron. So their most probable ion is a +1 because they lose that 1 valence electron to get a full octet. So I'm going to write down the symbol but also the charge when we're doing ionic formulas. This is going to help me figure out the subscripts. So for sulfur, sulfur is going to have a negative charge. Looking at sulfur, it's in group 16, right under oxygen. They are 2 away from having a full octet. So oxygen, sulfur, selenium, they have 6 valence electrons. They want 8. So they gain 2 electrons, making them a -2. So why are these charges going to help me? Because this compound, sodium sulfide, it's neutral overall. What that means is its positive and negatives cancel each other out. So I need to figure out how many of each I need to get an overall neutral charge. So looking at the charges now, if I have 1 sodium, I have a +1 charge on my cation side. If I have 1 sulfur, I have a -2 on my anion side. If I take +1 -2, does that equal 0? It's going to equal a negative. So what that means is I need more of the positive charge. I need another sodium atom. Because if I have 2 sodium atoms, now I have +1, +1, a +2 charge on the cation side. Now my sulfur, I have a -2. So now the charges cancel each other out and it's neutral. A +2 plus a -2 equals 0. So this tells me that my compound, my chemical formula, needs 2 sodiums. So I'm going to write Na with a little 2 after it, because I need 2 sodium atoms for every 1 sulfur. So this would be the correct chemical formula, Na2S. So a little more complicated than the covalent, where you just use the prefixes. So let's try another one. Let's look at lithium hydride. So start by finding the symbols and then writing the charges, their oxidation states, their most probable ion. So lithium is Li, group 1, alkali metal. So it's similar to sodium. They're in the same group, so that means they have the same most probable ion, +1. Hydrogen. So hydrogen's a tricky guy, because hydrogen can actually be a +1 or it can be a -1. So how do I know what it is in this case? I have a positive already. Lithium has to be a +1. And I said that I always need a cation with an anion for their ionic compounds. So that means that hydrogen must be a -1 in this case. Marker. So now, to figure out the chemical formula, looking at these charges, do they cancel each other out as is? This time they do, so that means I just need 1 of each. So my chemical formula is as simple as LiH. It's kind of done for me on that one. All right, let's try rubidium phosphide. So rubidium, where's that guy? Gosh, I'm kind of staying in the same realm. Rubidium, Rb, it's also an alkali metal. I'll have to do more examples where they're not alkali metals. Aluminum will be different. So rubidium, +1 as well, because all of these metals are in the same group. Phosphide is just phosphorus, so P. So the charge on phosphorus, it's 3 away from being a noble gas. It's in group 15. So it's going to gain 3 electrons. So everybody in group 15 is going to have a -3 charge for their most probable ion. So now, notice the charges aren't canceling. I have more negative than I do positive, so I need to add more rubidium atoms. If I add 1 more, now I have a +2, but I got to keep going because I got a -3 over here. So I'm going to add a 3rd one. Now I have a +3 on the cation side, -3 on the anion side, making that an overall neutral compound. So for the chemical formula, it's saying I need 1, 2, 3 rubidium atoms, so Rb3, and 1 phosphorus. So now that we've seen the charges, how we add them up, I'm going to show you a shortcut way. So I like to write it out this way because this is correct every single time and I can see what's happening. But there is a shortcut if you prefer, and what that shortcut is, it's called the crisscross method. And what we do with the crisscross method is we take the numbers, not the charges themselves, but the numbers present here, and we crisscross them. So this number 1, that's going to be the subscript on phosphorus. And this number 3, so not the negative sign, just the number, is going to be a subscript on rubidium. So what I'm saying is I need 3 rubidiums and 1 phosphorus. So same chemical formula. So you can do that as well instead of writing it all out. All right, let's try one without an alkali metal. So the last one I have up here is aluminum oxide. So aluminum, it's in group 13. So it's on that zigzag line, but it is a metal. So aluminum is Al, it's right below boron. And since it's a metal with 3 valence electrons in it, it's going to lose all 3 to become a +3 ion. Oxide, that's oxygen. So we're looking in group 16. So oxygen has 6 valence electrons. It's going to gain 2 more to get a full octet. So -2 is going to be its charge once it gains those 2 electrons. So we can do this in 2 ways. We can do the crisscross method, or we can write it out and see how many of each we need to get neutral compound. So either way works. Right now, looking at it, I have too many positives, right? +3 and a -2. So if I add another oxygen atom, now I have -4 and a +3. So I need another aluminum. So you just kind of go back and forth until they equal each other out. So I have a +6 and a -4, so I need more negatives, so I'm going to add another oxygen atom. And then now I think I'm finally there. So on the cation side, +3 plus a 3 equals a +6. On the oxygen side, -2 plus -2 plus -2 gives me a -6. So now it's neutral. Now notice you could have also done the crisscross method, where I need 3 oxygens, 1, 2, 3, and 2 aluminums. So both ways will give you the same answer. So I have Al2.
Oh, so you have to multiply both sides, like 3 times 2, and then other side equals 6. Like crossing.
For the crisscross?
Uh-huh.
Yeah, so the numbers here, are saying you need 2 aluminums for a total of +6, and then 3 oxygens for a total of -6. Is that what you're talking about,
Yeah.
multiplying the charges? Yeah. So you can still figure out that it's neutral using the crisscross method too. Any questions on this? You want to do more of them, or do you want to move on to polyatomics?
You can move on.
Okay. So we're still looking at ionic compounds. So all of this is going to be similar. We're just going to add a layer onto it. So instead of just metals and nonmetals, we're now going to look at polyatomics. So polyatomic ions. So polyatomic ions, you can have ionic compounds that contain a polyatomic ion. Notice the word ion. So what that means is these are covalently bonded compounds, but they have a charge. So since they have a charge, since they're an ion, they're involved in ionic bonds. Okay, so for the polyatomics, you have a list of common polyatomics on the same sheet as that electronegativity table. So you'll notice that all of the examples have 2 or more atoms bonded together, but all of them also have a charge. You'll also see there's a name next to them. So the name next to them, that's the name we're going to use when naming these compounds. Okay, we're not going to add ID endings, anything like that. We're just going to use it exactly how it is on the table. So best way, I feel anyway, to learn is to just try an example. Now you'll notice most of the polyatomics have a negative charge. So most of the time, the polyatomic ions are going to be in place of the nonmetal portion, because the nonmetal is the negative ion. And most of the polyatomics are negative as well. Not all of them. So let's look at a few examples. I'm trying to use different ones than the PowerPoints so that you get a variety, in case you're watching both. So we're going to do the same. We're going to take some examples and name them, and then we'll do the opposite way if we have time. All right, so BaSO4. How do I know a polyatomic's in there? Well, I know that it's ionic because of the fact there's a metal in it, barium. But how do I know a polyatonic's involved? Is because notice, so far, we've only had 2 elements present. There might have been several atoms of those elements, but every example we've seen so far have had just 2 elements. This one has 3. We have barium, we have sulfur, we have oxygen. So the fact that there's 3 elements tells me there must be a polyatomic in there. Okay, so just identifying the fact that there's a polyatomic, from there you can go to your table and figure out what it is. So when I look at my table, I'm going to find that this portion, the SO4, is the polyatomic portion. So SO4, it's the second to the last one in the second column. It says SO4 2-. That's a sulfate, so that's its name. So what that means is when I name this, I'm going to approach it like my other ionic compounds. I'm going to take the metal portion and name that first. So Ba is barium. And then SO4, since the polyatomic, I find it on the polyatomic table, and I just write the name of it, just how it's written on the table. So barium sulfate. I don't add an IDE ending, nothing like that. We only add IDE endings if it's a non-metal from the periodic table. The polyatomics would be just how they are. All right, so let's try the next one. So we have lithium, chlorine, and oxygen.
So we're not including the oxygen if we write the polyatomic ions. There's
Right.
oxygen, it's 3 oxygen. And
So
the first one.
This one?
Uh-huh.
So we have barium, sulfur, and oxygen.
Uh-huh.
So if we tried to name this without using a polyatomic, that would be difficult because which one, we said the first element you name straight from the periodic table.
Yeah.
The second element you do with an IDE ending.
Uh-huh.
But now we have a third element,
Mhm.
so we couldn't do how would we do that? Sulfur oxide? Do you see what I mean? So since it gets weird like that, we have special names if there's more than one non-metal. Does that make sense? So by recognizing there's more than one non-metal, then you go, oh wait, I can't name that my normal way, let me go to my polyatomic table.
Okay.
So that's what we're seeing in this example too. We have lithium, Li, the metal, and then we have 2 nonmetals. So how do we name that? Well, it must be a polyatomic. So this non-metal portion, we're going to look up in the table. ClO3. I don't remember what that one is even. So it's the 4th one down. So chlorate. Yes. So Li is lithium. And then this polyatomic in the table is chlorate. Now pay special attention because you'll notice there's a ClO3 and a ClO2. So they only differ by 1 atom and their names only differ by 1 letter. So just be especially careful when you're naming these, that you're picking the right one because they only differ by a small amount. So chlorate, ATE, tells me it's ClO3. Now this next one is kind of difficult because notice we have 3 elements, so we know polyatomics in there, but they're all non-metals. So you might think at first glance, oh wait, that's a covalent compound because those are all non-metals, but it's not. Okay, why? Because if you look up NH4, this has a charge on it. NH4 is the only positive polyatomic on your table. So it's the second one down, NH4 with a plus. So NH4 with a plus, since it has a charge, since it's an ion, this is an ionic compound. So NH4 is ammonium. Switch back to my black marker, that's okay. And then now we have it with chlorine. So chlorine's the second part, it's the anion portion. So we can't just write chlorine, we need to add that IDE ending just like we did for our original binary ionic compounds. So chlorine is going to become chloride, the IDE ending. Ammonium chloride would be the name for that one. So let's take these names and do some practice with coming up with the chemical formulas. So it's going to be that charge swapping thing again. And I did some examples in the PowerPoints and I never gave the answer. So I'm going to write that list of examples here and we'll figure out what the chemical formulas are. Sorry, I can't talk and write at the same time sometimes. Okay. That last example shows something here. All right, so potassium nitrate. It's an ionic compound. It has a metal involved. How do I know this second part is a polyatomic and not an element from the periodic table? It's the ending. If it was element from the periodic table, we have an IDE ending on it. This has an ATE, so I know it's going to be a polyatomic because of that. So we're going to do it the same way. We're going to write the symbols and their charges. So potassium. Potassium is an alkali metal. K is its symbol. Since it's an alkali metal, since it's in that first group, its charge is +1. For the nitrate, I've already identified it as a polyatomic. So now I just need to find it and write its chemical formula and its charge. So nitrate is NO3, and then it has a minus. There's no number after it, so we just assume it's a 1. So it is a -1 charge for nitrate. So how do we write this? First, we need to figure out how many of each we need. Do the charges cancel as is?
Oh, no.
Yeah, +1, -1, that equals 0. So that means we just need 1 potassium and 1 NO3. So we just put them together, KNO3. So started with an easy one. Let's try a harder one. These charges aren't going to cancel. Aluminum never does. Aluminum is that metal that is touching the zigzag line, group 13, has the +3 charge. So Al +3, that would be its symbol and its charge. Sulfate. ATE tells me most likely polyatomic. So look up sulfate on your polyatomic table. And I get SO4, and the charge on that is -2. Now the charges are not canceling. So I can do the crisscross method, or I can keep adding ions to figure out how many I need of each. Okay, I'm going to do the crisscross method. That means I need 3 sulfate ions and 2 aluminum ions. So what does that look like? I just said I needed 2 aluminum, so Al2. 3 sulfate ions. So here's the thing with polyatomics. If there's more than 1, I don't want to just put my 3 there after the 4, because then it looks like I have 1 sulfur and 43 oxygens. That's bad, right? So instead, what I'm going to do is I'm going to put parentheses around the entire polyatomic and then put my 3 outside of the parentheses, because now it's saying, okay, I have 3 sulfates, so I have 3 sulfurs and 12 oxygens. Much better. So don't forget that parentheses, because otherwise it's going to be wrong, incorrect, right? You don't want 43 oxygens. All right, so this last example, strontium sulfide. Notice the ending, IDE. So This is not a polyatomic. Okay, there are a few polyatomics with IDEs, but for the most part, they don't. So the ones that have IDEs, I think is just cyanide. I think is the only one. Yeah. But otherwise, IDEs tell you that it's from the periodic table. So I wanted to throw this one in there just so you can see the difference. So we're still doing the same process. We're still going to write the ions, their charges. So strontium, strontium's SR, it's alkaline earth metal, in group 2. So since it's in group 2, it has a +2. And sulfide is the IDE version of sulfur. So we're looking at sulfur in group 16. Sulfur is an S, and it's going to have a -2 charge. So on this one, this was an easy one too, because the charges cancel without having to add more ions to either side, so it's just SRS. Kind of a weird looking chemical formula. But I just wanted to do this one so that you notice the difference, because they're not always going to tell you, hey, there's a polyatomic in here. They'll just say, name this ionic compound. And so you'll need to figure out, based off of the endings, if there's a polyatomic or not, so that you can look in the right place, get off on the right foot. All right, I don't want to get into transition metals yet. Do I? Oh, no. Do you have any questions on this? Do you want me to do more examples?
Yeah.
More examples?
Yeah.
Okay. I didn't want to start transition metals because that's kind of a whole nother ball game. That'd be a little weird. So. I'm just making up ones on the fly so it's okay. So I have a hodgepodge. These are all ionic compounds. So we're going to figure out if there's polyatomics involved or not and come up with chemical formulas. So looking at potassium nitride, do you think there's a polyatomic in that one?
Yes. Yes. Oh, no. No.
You're looking at the endings, right? So IDE, most likely not, okay? But let's find the symbols and see. So we'll go from there. So potassium, that's an alkali metal in group 1. K is its symbol. Since it's in group 1, it's a +1. So nitride, the IDE ending tells me that it's just nitrogen with the IDE. So I'm just looking at N. Now nitrogen's in group 15. So remember, just like phosphorus, it's 3 away from being a noble gas, so 3 away from having a full octet. So it's going to gain 3 electrons for a -3 charge. Is the crisscross method okay with you, or do you want to write it out?
No, cross.
Crisscross is fine? Okay. So we'll do the crisscross. So we're going to take the 3 is going to be a subscript on potassium, and then we just need 1 nitrogen. So this becomes K3 and then N. Don't include the 1, just leave it as N. This next one is a little tricky. Okay, we have magnesium cyanide. So we do have an IDE ending. So that usually tells me that it's an element on the periodic table. But in this case, it's not. It's a polyatomic. Well, how do I figure that out? Well, cyan is not an element. So that's a clue. And obviously, you probably don't know every element on the periodic table yet. So if you're trying to find where cyan is and you can't find it, your next place to go would be to look at the polyatomics. And cyanide is a polyatomic. It's one of the only with an IDE ending, so that would help you remember it too. So we're going to write magnesium, find that guy with its charge, and then we'll write cyanide, its symbols with its charge, and just go from there. So magnesium is an alkaline earth metal. It's in group 2. It's Mg. Since it's in group 2, it forms a +2 charge by losing 2 valence electrons. Cyanide, once I realize it's a polyatomic and find it on the polyatomic table, it's carbon and nitrogen together, and it has an overall -1 charge. So, because of their charges, I'm going to need 2 of the cyanide ions and just 1 of the magnesium ions. So if I write it like this, is that correct? Because I put my 2 here, but I need 2 of the entire ion. So remember the polyatomics. Here I'm saying I have 2 nitrogens and just 1 carbon, but I don't want that. I want 2 of both of them. So I need to make sure that I'm doing my parentheses and the 2 outside of the parentheses. Okay, so magnesium, Cn, and then the 2 outside. Because that way I have 2 cyanide ions. So polyatomics, if you have more than 1, parentheses every time. That's the most common mistake. People just putting the number there and not including the whole polyatomic. Okay, sodium acetate. We got an ATE, so it's definitely a polyatomic. Sodium, alkali metal, Na, +1, group 1. Acetate, we would find that on a polyatomic. This is a big guy. Is it C2H3O2? So that's acetate. 3 different nonmetals bonded together with a total -1 charge. This one, charges cancel. You just need 1 of each. So you have sodium with 2 carbons, 3 hydrogens, and 2 oxygens. So this would be the chemical formula.
Because they cancel the.
Yeah, they cancel each other out. So, I mean, you could do the crisscross too and see that. You just need 1 sodium and 1 acetate. I almost called that oxalate. So the last one, ammonium oxalate. So a lot of these, they're going to be confusing at first until you get used to some of the names. The more you practice these, the more you're going to recognize, oh, those are polyatomics. Because what I have here, the tricky one about this, ammonium is not a metal. Ammonium's actually a polyatomic. And then oxalate, we can identify that as a polyatomic just because of the ATE ending. But the first one, that's kind of hard, because at first you're like, oh, the metal, where is it? But ammonium's not a metal, it's actually a polyatomic. So you can have an ionic compound made up of 2 different polyatomics bonded together. The only thing that's necessary for an ionic compound is to have a positive and a negative ion together. And that's what we have here. So let's look, and erase this to make some room, at what this chemical formula is going to look like. So we're going to find both of these polyatomics on the table. We're going to write their element symbols with their charge. So ammonium is our only positive one on that table, NH4 with a +1 charge. And then oxalate, I forget what oxalate is, C2O4?
C2O4 negative.
Or -2, you can write it either way. So here, the charges aren't canceling, So I need more ammoniums, right? I need 2 ammonium ions for every 1 oxalate. So when I write, get new black markers. When I write NH4, I just said that I need 2 of them. Since NH4, ammonium, is a polyatomic, you do want parentheses and then the 2. Otherwise, it's going to look like I have 42 hydrogens. So NH4, 2 of them, and then the oxalate, we said just 1. So we don't need parentheses around that portion. We can just write C2O4. So it looks very complicated, but its name is very simple. Ammonium oxalate. We're just naming the 2 polyatomics that are together.